Hey folks, welcome to Chapter 3 of Physics 11. We are looking at vectors in this chapter. Now, really quickly, before we even jot down sort of what vectors are, this chapter is going to have a whole bunch of trigonometry. We're going to be drawing a lot of different triangles. So just really quickly, to be honest, I don't even know if you need to write this down. But a little bit of trig review. We're going to start the first couple of lessons doing nothing more than SOHCAHTOA. And that's all this picture is showing, is it's just showing us nice right angle triangles. We've got theta, an angle right here. We need to know that there is an opposite side. Hypotenuse is the longest side. I actually find those two easiest to label first. So go opposite the angle, hypotenuse is your long side, and then the leftover side is adjacent. And then your different trig ratios, so sine opposite over hypotenuse, cosine adjacent over hypotenuse, and TOA, tan, which is opposite over adjacent. You will need to make sure that your calculator is in degree mode. So maybe as you're going through this video, double check with my calculations that yours is matching. You don't want to get all these things wrong and have it be an exercise in frustration because you're in some other mode on your calculator. So this is a little trig review showing how you can solve for different angles, and you can also solve for sides. So if we take any of these equations, you could rearrange them to solve for the adjacent side or the hypotenuse. For example, if you want to find an adjacent side, that could be something like taking this first equation here, cosine theta, multiplying both sides by hypotenuse. So pretty darn straightforward. I think there's one more. Yeah, you could find an opposite side by taking the hypotenuse times sine theta. And that pops up the odd time too. You'll see it in this lesson coming up. But that should be easy, I think, I hope. What we really want to get into is vectors themselves. Dig in a little bit here. Do remember that we talked about vectors in Chapter 2. These are measurements that have a size in units, but the really important part here is direction. And what we're going to do in this chapter is we're going to go a little bit further than we did in Chapter 2. We're going to make them two-dimensional in Chapter 3. So instead of just positive and negative, we're going to start talking about vectors relative to a compass. We're going to throw in norths and souths and easts and wests. And when we draw them, I mentioned we're going to draw these little triangles. We're going to use arrows to represent vectors. We always want to keep track of which way the vector is pointing. So we're not going to draw just a line, because a line could be pointing out either end. We're going to draw an arrow that is very specifically pointing in one direction. So the first game we're going to play here is just talking about sort of angles. So here we've got a compass rose. I sometimes call it compass crosshairs. North, east, south, west. Never eat soggy wieners. There's probably some little memory device you have for that. So here we've got a vector. Remember the vectors we've talked about have been displacement, which would have units of meters, velocity, units of meters per second, and acceleration, units of meters per second squared. So don't be surprised to see any of those in this chapter. But here we've got this vector, it's 18 meters. That part's easy. What we have to sort of figure out right now is what's the angle look like? Is that 20 degrees north of east or 20 degrees east of north? Because it actually turns out that those two angles take you to totally opposite places, or totally different places, I should say. So this vector here is worth 18 meters. The angle piece we typically put in square brackets, although if you really like round brackets better, you could do that too. So this is 18 meters at an angle of 20 degrees. Now, to figure out which way we're going to label this, is it north of east or east of north? It has nothing to do with how big that angle is. Sometimes students think, oh, it's bigger than 45 or it's less than 45, so it must be this. That part actually doesn't matter. What does matter is if you were to take like a bicycle pump and stick it in there on the 20 degrees and inflate the 20 degrees and make it 30 degrees and 40 degrees and 50 degrees, which direction would it push this green vector if the 20 were an inflatable angle? And you would say, well, it would, I guess, push the thing this way. We'd be pushing that vector towards the north, away from the east. So north goes first. So that is north of east. And that game then, we don't write this in, but that means 20 degrees. And then if we inflate it, it goes towards the north and it goes away from the east. We're getting further and further away from the east side. So let's try another one. I'll throw one more in here. We'll color code. Let's go purple. Let's go with this one. Let's go right down there. Let's call this 10 meters, and let's go 33 degrees right there. So this vector has a size of 10 meters, but the direction piece is important. This is 33 degrees, something of something. We need to figure out how to fill in those blanks. And in this case, imagine inflating the 33. Make it 43, make it 53, make it 63. Which direction would we be pushing that purple line? Well, we'd be pushing it that way. We'd be pushing it towards the west. So west is going to go first. That is west of south. Not south of west, but west of south. Now, in case you're wondering, there is something in math that you sometimes talk about, and that's called a reference angle. The reference angle is the other angle that adds up to 90. So it would be this angle in here, right there. So there is another angle that would also work. That, I guess, would be 57. 90 minus 33. So another acceptable answer, if you wanted, would be to call that 57 degrees, but not west of south. If you inflate the 57 to make it 67, to make it 77, you'd be pushing that way. You'd be pushing south of west. So that's the reference angle, and either of them works. I'll take either on a quiz or a test or an assignment. But do notice the reference angles have opposite direction. One's going to be, in this case, west of south, while the other is south of west. Okay, let's talk about how to add vectors together. What we do, we draw little, we call them vector diagrams, little pictures, and we are going to add vectors by connecting the arrows head to tail. So I'll show you what I mean. We want one arrow to sort of blend into the next, So let's start out with something really easy that probably doesn't even need a diagram, to be honest. If you walk 8 meters north, and then stop, maybe you give a friend a high five, and then you walk another 5 meters north, what we're trying to figure out is what is your overall trip? What is your displacement? Well, Heinrich, it's just 8 north and 5 north. Isn't that 13 meters north? Yeah, it is. It's that easy. Here's what it might look like in a picture if you wanted a picture for this one, although I don't think you need it. You walk 8 meters north, you stop, so we put a little arrowhead on that, and then you keep going another 5 meters north, put an arrowhead on that. Your overall trip becomes that red line. In physics, we call that the resultant when we add vectors together, and it's the result of adding the vectors. Notice these vectors are head to tail, so the head of one vector touches the tail of the next one. That's how we want to add. In this case, the picture wasn't really necessary. We walked 13 meters north. That's simple. Let's look at one where a diagram would actually be really helpful. And that's something like this. What if you walk 12 meters west and then you turn 90 degrees and you go 5 meters to the north? So we want to figure out if you walk 12 meters to the west, notice I put an arrowhead on that because we have to know whether we're going west or east. And if there's just a line with no arrowheads, then it's a crapshoot. Which way are we going? We can't tell. So 12 meters west, and then we've turned, we've gone 5 meters to the north. The resultant always goes from where you started your trip to the end, to right there. So the resultant is, if you've heard the saying, as the crow flies, it's like the shortest distance from the start to the end, the displacement. So the resultant would look like that. So we're going to draw this resultant line saying, hey, there's the straight line distance from start to finish. And then we need to solve for that side to figure out what is that displacement. And then we also want to put the angle in the corner where we started, which is right there. We want to figure out how far did we leave from our starting position, and at what angle did we go from that starting position. So that theta is always going to go in the corner where you started. Now, looking at that triangle, we can solve for x by running some Pythagoras. A squared plus b squared equals c squared. And we're solving for c squared, the hypotenuse. So there's what the math looks like. You can pause it and scribble that down if you want. We get a nice number. We get x equals 13. I'm not going to worry about units or anything yet because I'll put all that together at the end. If we want to solve for the angle, the safest bet is to probably use tangent. Now, I guess you could use tan or sine or cosine because we know all the sides. But I think tan is the safest because if we didn't get the 13 right, now we've gotten this part of the question wrong as well. We're doubly wrong. So it's safer, I think, to go with the numbers that are just given to us in the question, which is tan. Don't forget you are actually doing an inverse tan to find an angle or a second function. And this is where you want to try it out on your calculator. You should get 23 degrees if you type that in. And if you don't, then you're probably in like radian mode or something, and you want to be in degree mode. You can always send me an email and we can figure out how to swap your calculator around, or just hit a reset button on the back, the mode button on a graphing calculator, or just, I bet you can Google search it and figure out how your calculator works. But I'm happy to help you. So let's put all that together into a final answer. We have moved 13 meters. That part's easy. At an angle of, we got the 23. That part wasn't too bad either. And now we have to figure out what the direction piece is. Something of something. Now in this case, you know it has to be west of north or north of west. One of the two. We're in that sort of quadrant of our compass rose. And you have to imagine inflating theta. If we make theta bigger and bigger and bigger, if we can pump it up with a little bike pump or something, an air compressor, we would be pushing the green resultant that way. And that is pushing towards the north, leaving the west. So that one would be 23 degrees north of west. Also acceptable would be, what would it be, 77? 77 degrees west of north. That would be the reference angle, and that works. But in this case, the way we've drawn the diagram, 23 degrees north of west. Now, what about subtracting vectors? It turns out we don't really subtract. We're going to do something kind of cool that you already know how to do. We're going to do something called add the opposite. So subtracting vectors actually turns into adding vectors. Here's an example. You walk 8 meters east, and then if you were to take away 2 meters east, what's another way of thinking about that? And if your brain works like mine, sorry, this is a scary thought, you might say, well, 8 meters east and then taking away 2 meters east, isn't that like adding 2 meters west? And the answer is, absolutely it is. So here's what we do. We don't ever actually subtract vectors. We change a subtraction into an addition, and then we switch direction on the number that's being subtracted. Not on the first number, just after the subtraction sign. So that becomes plus 2 meters west. Now I think I probably have a picture in these notes, but I don't think you need it. If you walk 8 meters east and then you walk 2 meters west, those are sort of like directions, if you want to call it that. What we've done is we have gone, yeah, sorry, I do have a picture. Don't even worry about sketching the diagram for this one. you've gone 6 meters, 6.0, let's get our 2 or 3 sig figs, 6.0 meters to the east. So that's easy. Let's skip through that example because it doesn't matter. Let's go to this one. What about 16 meters per second west minus 12 meters per second south? Good try, Heinrich. We don't actually subtract vectors. What we do is we change it to an addition and we swap that direction. So south becomes north. So I like to just hack that right out of there and say, nope, now it's a west and a north being added together, and now we're back to drawing a nice little vector diagram. So 16 meters per second west. West is to the left. Make sure you catch that. Sometimes people get the east and the west mixed up. So 16 west, turn and pivot, go 12 north. We're looking for the size of the resultant and the angle. The angle always goes down in the corner where we started, which is right there. A little bit of Pythagoras to solve for x. There's the value. You can do it on your calculator or not. You can probably do Pythagoras all day long. We get a nice number. We get 20. And then we're going to want to run some trig, and I would go with tan again as the safest bet. Try to stay away from using the 20 if we can. So if you run tan, which actually ends up being a second function or inverse tan on your calculator, you're going to get 37 degrees. And if we put all of that together, that is 20, now it's meters per second. Looks like we were adding some velocities together at 37 degrees something of something. So if you inflate theta, stick a bike pump on it, pump it up, which way does the increasingly big theta push that x vector? Well, it's going to push it that way. It's going to get bigger and bigger and bigger, pushing towards the north, leaving the west. So that way that we've drawn the picture is a 37 degrees north of west. Now, what about this scenario? What about if you move more than just like 2 different directions? What if you go north and then west, and then you subtract a north and you add a 2 west? Hopefully there's something you can sort of notice in there right away where you go, nope, I don't like that. And that's the subtraction. So that's maybe the first thing I would do. Looks like we're adding some things, but then we've got that silly little subtraction in there. We don't actually subtract. Cross it out. We add the opposite. So we've got a 3 meters south we're going to add instead of subtracting a 3 meters north. Now, what do we do when we've got these like 4 movements? Well, what I would do is I would maybe add the like directions, or like terms if you want to call it that. So let's add the norths and souths, and then the easts and the wests, and see what we have overall in each of those directions. So in the north-south direction, we've got a 1 north and a 3 south. That's going to give us 2.0 meters south. And in the east-west, it's actually just a couple of wests being added together, a 6 plus a 2. That's going to give us 8.0 meters west. And now what we're going to do is we're going to add those. So we combine like directions to get it down into just 2 simple directions. And now we add them. We've got a south, we've got a west, so that's going to be a triangle. So it might look something like that. 2 meters south and then 8 meters to the west. We want to know what that resultant is. So we traveled out in this direction. We need to solve for the size of that and the angle of that resultant. And what have we got? Pythagoras again. I guess I'll just sketch it really quickly here. X squared equals 8 squared plus 2 squared. I think my notes got a little bit confusing if I page down, so I'll just do it here with you. X equals the square root of 8 squared plus 2 squared, 8.25. And I think our safest bet is going to be a tan theta. Opposite over adjacent is going to be an 8 over 2. And it's actually going to be a second function when you go to type that in your calculator. So second tan, 8 over 2. Looks like 76 degrees. And if we put all that together, units are just meters. So we're looking at an 8.25 meters at 76 degrees, something of something. Make theta bigger. Which way does it push that dotted line? Well, it's going to push it that way. That is pushing us up towards the west. So this is west, leaving the south, west of south. Okay, last bit of this lesson is something that we need to know for chapter 4, an important skill. And that's kind of undoing what we've been doing with vectors. And that's something called resolving vectors, where you take a vector that's already at an angle and you break it up and figure out what its short sides are, instead of taking the two short sides and figuring out the angle. We're going to go backwards. We're going to do the opposite here. So let's just make up a number here. Let's go, actually, I might have one in here that works. Yeah, let's try this. Pardon my spacing. Let's try 4.35 meters per second at 28 degrees north of east. So what you're going to want to do is get a vector drawn, generally pointing north and east. So it might look something like that. Don't worry about using a protractor or something. We're going to let the math sort itself out. So that vector has got a size of 4.35 meters per second squared. Now we're going to turn this into a triangle, but there's kind of two triangles that are potentially possible. I want you to see if you can figure out which of them works, because only one does. We have got 28 degrees north of east. So here's one way we could close it in. We could close in the diagram this way. Don't draw anything yet, because only one of these is going to work. So we could close in our triangle like that. Is that 28 degrees north of east? Or does it look like this? You could have your 28 on the top side, and then our triangle would close in this way. So you have to figure out at 28 degrees north of east, which of those 28s is the one we're looking for. Remember, that's 28 degrees pushing towards the north. Which one of those pushes towards the north? Well, it's this one here. It's the blue one. So I'm going to take this one away, and then you can sketch it in there. That's your vector diagram. And what we want to do is we want to solve for the two short sides. So you can label them as like x's and y's. Some people do that, like the axes on a graph. I'm actually just going to call this one n for north, and this one e for east, just to make life easy. And now we're into some SOHCAHTOA in a slightly different way to solve for those two sides. So, for example, to find north, I can use sine of 28 degrees. That's equal to opposite, which is north, over hypotenuse, which is 435. Now, in terms of the math, to solve for north, we're simply going to multiply both sides by 435 times 4.35. And if we grab our calculator, 435 times sine 28 looks like 2.04. For units, just look back at what we had in the question. Meters per second squared, and the n was telling me that that thing is pointing just to the north. Now to solve for east, I'll switch colors here. The trig ratio we want, probably a cosine. So cosine of 28 is your adjacent side, which is east, over 4.35. Multiply both sides by 435. Cancel on that side, times 435. Grab the calculator. 435 times cosine 28. Not a second function cosine or sine this time, just regular old sine and cosine. We get 3.84. 0.84 units of meters per second squared, and that is pointing east. There you go. Now, give me a second. I'm going to pull up the homework that I want you to try based on this lesson because you've made it to the end. Okay, here's what I want you to try for homework. Worksheet number 1, numbers 1 through 7. That's what you can try. 8, 9, 10, 11, 12, optional. Above and beyond what you're going to need to know for Physics 11 this year, which means you probably don't need to worry about those. So try numbers 1 through 7. Answers are on the back of the blue chapter outline. If you need some help with any of it, get in touch with me. Have fun.